So today I am going to discuss different methods of circuit analysis. So by applying Ohm's law, KCL, that means Kirchhoff's current law, and KVL, Kirchhoff's voltage law, we can find out or we can do the analysis of a circuit. So let us take a circuit in general where total number of elements are B, number of nodes are N, and number of loops are L. Now for a circuit where number of elements B, number of nodes N, and number of loops are L, for this kind of circuit, if we see the number of elements has how many variables? Electrical variables. There are two electrical variables, voltages and currents. Let us take one electrical element which is having voltage drop across it is V and current flowing through it is I. So these are the two variables for a circuit element, for any circuit element that we can give. So based on that, if any circuit, if it has B number of elements, so how many variables will be there? So total number of variables, will be 2 times B, because for each element there will be two variables, one is V, another is I. So now to get the value of these two B variables of a circuit, what we can do, we need to have some number of equations, that is total 2B number of equations are needed to calculate or to find out the values of the variables. So therefore now we will see that to find out or to determine the values of 2B variables, we need 2B number of equations. So from where we will get this 2B number of equations? Out of this 2B number of equations, we will get from KCL and from KVL. Now as we all know that KCL, that is Kirchhoff's current law, that we apply at the nodes to write down the equations or to write down the equation of currents which is coming to the node. Similarly for KVL, we write down the voltage equation where the equation we get by applying the law or the Kirchhoff's voltage law to a particular loop. So here if we see for a circuit, then the KCL that we are applying to a circuit at all the nodes, then there are n number of nodes in a circuit. Okay, but we can apply the KCL to all the nodes, all the n number of nodes. But if we apply the KCL to all the n number of nodes, then there will be one redundant current equation that will be coming. So to eliminate that redundant current equation, what we do, we apply KCL to n minus 1 independent nodes. So for this case, what we do, we take one node as the reference node in the circuit and we apply KCL to all the other non-reference nodes. Then we find out n minus 1 number of independent equations. So we apply KCL to n minus 1 independent nodes to write n minus 1 for n minus 1 current equations. Similarly, we can apply KVL to all the loops in the circuit, but out of all the loops there is one loop that consists of many other loops. So here we will take n minus means b minus 1 independent loop. So we will apply KVL to b minus n plus 1 independent loops for voltage equation. So now the rest of the equation, so b number of equation we have got from KCL and KVL, and rest b number of equation that we get by writing down element equations so as there are b number of elements, so for each element we will write down the relation of voltage current for all the elements. So we will get b number of element equation for each and every element. Let us say, as for example, we can say that if there is one resistor, this is an element of a circuit which is having the resistance R and the current that flows through the resistor is I. So the voltage that is dropped across the resistor is V. So the element relation that we can write for this resistor is V equal to Ri. So this way for all the elements we can write down the element equations. Likewise, if we say that there is a voltage source, independent voltage source in a circuit, which is supplying the voltage say V1. So for this particular case we can say that this V1 is equal to some constant value K, because this is a independent voltage source. So this way, for each element we can write down the element equations. So this way, if we form or if we write the total 2b number of equations, so from these 2b number of equations, if we solve, then we will be able to get the values of all the variables. So now from this basic way to analyze the circuit, if we see, then it is seen that there are a number of lot of equations are needed to get to know the variable values of a circuit. For a say for a circuit where there are 10 elements, so for 10 elements there will be 10 number of, means 10 into 2, 20 number of variables. For 20 number of variables you need to have 20 equations, and then you have to solve all the 20 equations, and then only we can get the values of all the variables. So now 10 number of means 10 element circuits, circuit is a small circuit, not that much large circuit. So for the larger circuit it will be a very tedious task to find out the values of the variables for the circuit. So therefore we go for some modifications. So that is why we have some other methods which are called as node voltage method and mesh current method. And that node voltage method and mesh current method has been derived from this basic way to analyze the circuit. So now next I will be discussing that node voltage method and mesh current method in brief. So now I am going to the next. So I will discuss this node voltage method and mesh current method like comparison. Okay, so node voltage method and another method is mesh current method. So in node voltage method, there one new term that come over here, that is called node voltage, and another term for mesh current method, there is one new term that comes, that is called mesh current. Previously here what I discussed, the method of doing the circuit analysis using KCL, KVL and the Ohm's law. So for that case, the voltages or the currents that we take over here, like for KCL the current equation, or the KVL, for the KVL the voltage equations. So all the voltages and currents are where the currents where branch current or element current, and the voltages were the branch voltages or element voltages. Now next, for node voltage method and mesh current method, this node voltage and mesh current is somehow different from the branch voltage and the branch current. So first let us see what is that actually. So now I have taken a part of a circuit where there are three resistors R1, R2, R3 are there, and the branch voltage or voltage across the elements of R1, R2, R3 are VR1, VR2 and VR3 respectively. And here this point or this node is the reference node as marked over here, and there are other two non-reference nodes we can see here, that is of voltage VA and of voltage VB. These voltage VA and VB, these are called branch voltages, node voltages. And now this VR2 and the branch voltage are VR1, VR2 and VR3. So these are the branch voltages. Now by applying KVL in this particular loop, if we apply KVL, then if we apply KVL, to this loop, then by applying KVL, what we can write is that minus VR1, if we take the clockwise direction, so according to the polarity of voltage drop across the elements, VR1 minus VR1 plus VR2 plus VR3 equal to 0. So by applying KVL to this particular loop, we can write down this voltage equation. Also from this circuit here we can see that this VR1, this is the voltage drop across the resistor, and what is the voltage difference across the resistor in terms of this node voltages? This VR1 equal to VA minus, for the reference node the voltage is 0, so this VR1 will be VA minus 0 volt, that is VA. Similarly this VR3 that is equal to VB minus 0, that is VB. So now if I put this VR1 and VR3 over here, then we can say that VR2 equal to VA minus VB. So from here what we can write? VR2 equal to VA minus VB. So now what we can say from this is, by applying KVL equation, we can say that the element voltage or branch voltage can be represented by the node voltages, and this is the way we can see that all the branch voltages are represented by the node voltages. Similarly, if we see the mesh currents, so these are the three elements present in a circuit. I have taken a part of a circuit, and let us say that splitter to so now I am taking one T arrangement for this. So let us say that for this through this R1 resistance, the element current is say IR1. For this, the element current is IR2, and for this R3 element, the element current is IR3. Now, mesh current is the current flowing in a particular mesh, or current flowing in an independent loop. So let us take this one as one independent loop. This is one independent loop. So let us say the current over here is say the current for mesh 1. Let us say the current is I1, and for this mesh the current is I2. Now here by applying, so in comparison with the node voltage method, so similar way, if at this particular node if we apply KCL at this particular node that I am showing over here, so applying KCL, what we can write? We can write that so I am considering that current going into is positive and current going out will be negative. So IR1 equal to IR2 plus IR3. So now here we can see that this I1 current that is also flowing, also the only current that is flowing through this resistor R1. So therefore this I1 current means IR1 will be equal to I1, and similarly through the resistor R3 there is only this I2 mesh current that is flowing through this R3 resistor. So therefore this IR3 will equal to I2. Now putting this IR1 and IR3 in this equation, what we can write from here is IR2 equal to I1 minus I2. So here from this, what we can say? We can say that all the branch currents can be represented by the mesh currents. So now what later what we can see is that for this node voltage method, if we go through, then and if we follow the procedure of this method, then we will see that by applying KCL and element method, we can write so here I am writing that that observation that we can see once we apply the procedure of node voltage method for any circuit. So applying KCL and element equations, n minus 1 node voltage equation we can write n minus 1 node voltage equation. So by solving all the node voltage equation, what we can get, we will get the node voltages. So let us say for the, if there are n minus 1 non-reference node, so for all the n minus 1 non-reference nodes, we will first define the node voltages, and then we will apply KCL and element equation together to write down the n minus 1 node voltage equations. So number of equations that will be needed for solving the circuit will be reducing to a very less number of equations, that is n minus 1 number of equations. So that is based on the number of nodes. How many nodes are there? Minus 1, that will be the total number of equations that will be needed to get the node voltage values. And once we get the node voltage value, then all the currents and all the variable values that we can find out. Similarly, for mesh current method, again what statement we can give if we apply the method means procedure or steps of the method, mesh current method, then we can also write that applying KVL and element equation we can form B minus n plus 1 mesh current equation. So in any circuit, if we are applying that mesh current method, then the number of equations that will be reduced from 2b to b minus n plus 1 number of equations for solving the or for finding out the mesh currents of the particular circuit. And once we get all the mesh currents, then from there we can find out the other voltages or other variables that are need to be find out. So this way, by applying, or these are the derived form of the basic methods of applying KCL, KVL and Ohm's law. These are the derived forms or derived methods, where we can see that these methods are what they are doing, they are reducing the number of equations needed for solving or for analyzing a particular circuit. Now go for the node voltage method. So now I am going for a node voltage method, and at the same time I am also going to show you the mesh current method. So I will take a particular circuit for node voltage method, and then directly I will show you that how in matrix form we can, by observing the circuit, how can we write the equations in matrix form directly. So for that, So for the node voltage method, I have taken a circuit, a very simple circuit, where I will show you that from the circuit how can we directly write down the voltage current relation or voltage current equations of the circuit, which are the node voltage equations. Okay, so for that, first, as you all know that while we are applying node voltage method to any circuit, first we have to mention the reference node. So let us take, so as this particular node is having three sources which are connected, means most number of sources connected to this particular node. So therefore this node I will take it as a reference node. And now all the other non-reference nodes that I will mention over here with their node voltages. Let us say the node voltages are VA, VB and VC. So there are three non-reference nodes which are named as, say, A, B and C, and the node voltages that I have mentioned already, that is VA, VB and VC. Now what method we can apply for node voltage? We can apply KCL to all the non-reference nodes. Like for this A node, B node and C node, we can apply KCL and then we will get three equations. But directly by observing the circuit, we can write down the matrix. Matrix means that is in the form of G into V equal to I. So G is the conductance matrix and V is the node voltage vector and I is the current, means the sources which are connected to the particular nodes. So in this form I will write the equation. So now here if we see that for this, means how many nodes are there? There are three nodes, that is VA, VB, VC. So three node voltages. So first we write down the three node voltages as VA, VB and VC. Now I will see that here, as this is one 3 cross 1 matrix. So to get the multiplication, we should be having a 3 cross 3 matrix over here. So there will be total 9 elements present in this G matrix. So this will be the G matrix or conductance matrix, where I will just show you that how the elements that we can calculate by observing the circuit. So first we are going to get the conductance values of this particular position. So this position is of AA. Now AA means that self-conductance. That means what are the conductances which are directly connected to the particular node, that is AA node. So if we see that for this A node, only one conductance which is G1, which is equal to 1 by R1, what we can write conductance equal to 1 by resistance. So we can write it as 1 by R1, conductance value or the conductance which is connected to the node 1 only, sorry, node A only. Now this position, now I will go to the second position, that is of position AB. So for this AB, we will see that what conductance value is mutual of this A and B node. So for this A and B node, the conductance that is mutual is 1 by R1, and we have to put the value of 1 by R1 or put that 1 by R1 with a minus sign in front of it. So it will be 1 by minus 1 by R1. Now the third one, that will be AC. That means what conductance is directly connected between or mutual between these two nodes A and C. So what we can see here is that A and C, these are the two nodes which are not directly connected. So therefore there will be no direct conductance value that is provided. So therefore we will put a 0 over here. Similarly, for all the other rows, we can write it as this position is of BA position. That means between B and A what conductance is present. So again this is the mutual position. So the value of the conductance that you have to put with a negative sign in front of it. And then this position is for BB. Now for BB, that you can see over here that there are three conductance values which are connected to this to the node B. One is 1 by R1, second one is 1 by R2, and third one is 1 by R3. So therefore we can write it as 1 by R1 plus 1 by R2 plus 1 by R3. And lastly here you can see that will be BA, BB, and this one is BC. So for BC, again there is R3 present, resistance. So it will be minus 1 by R3, that is the conductance value with minus sign. 1 by R3. So this way if I write the third row, it will be CA. CA, that means there is no direct connection in between. So therefore the conductance value will be 0. Then CB, so the connection is minus 1 by R3. This is connected by this 1 by R3. And the last one is CC. So for this C node, only the resistance connected is 1 by R3. So the conductance value will be 1 by R3. So this way we can write the G matrix, and on the right hand side what we can write is that the current that is going into, that is over here I1, okay. For this particular case I have missed one node over here, okay, but change the circuit. So this is the circuit. For this whatever matrix form I have written, that is okay. So here on the right side what I can write is at this node A it will be current that is going into, that is minus I1, and here also it is going into, so that will be minus I2. So what are the sources that are connected to that node, that we have to write on the current vector, and this one is. So this way, this is also a 3 cross 1. So this way we can directly write down the 3 equations, as I have said in the last slide, that there will be needed total n minus 1 number of equations if we apply KCL to all the nodes, and along with if we apply the element equations, so direct we can get n minus 1 node voltage equation. So as we can see, there are total 1, 2, 3 and 4 number of nodes, so 4 minus 1, so 3 number of equations will be formed once we apply node voltage. So here are the 3 equations which are in matrix form. So similarly for the mesh current also, if we follow the mesh current methods. Similarly, for this mesh current method, what first we have to take? We have to take how many independent loops are there. So in this circuit there are two independent loops. So first we have to mention the loop currents like I1 and I2. Then we have to write the matrix form, but that we will write here in this V equal to R or so R matrix into I vector equal to V vector. So in this form we can write down the mesh current equations directly in matrix form. So therefore first thing, directly to write down the equations over here, first we have to put the currents, mesh currents. One is I1 and another is I2. Then on the left hand side again we have to check that what are the resistances which are connected to this particular mesh, sum the resistance values and put it in this position. So there will be this is a 2 cross 1 matrix. So this R matrix should be of 2 cross 2. So therefore there are 4 locations or 4 elements that will be there. So this is element 1 1. So that means what are the resistances that are connected to this, means they are the part of the particular mesh that we have to sum up. So here you can see for this first mesh, the R1 and R2 are the two resistances which are the part of this particular loop I1 or mesh I1. So we will write it as R1 plus R2. And next for the next element, it is the element that is 1 2. Okay, so that is what is the mutual element the element which is common for both the meshes. So that common resistance value that we have to give with minus sign. So this R2 is common for this I1 and 2 mesh, so it will be minus R2. Similarly, this position is of 2 1. So if I write down the position, then it will be 1 2 1 1. Sorry, this is 1 2 position. This is 2 1 position. This is 2 2 position. So for 2 1 position again, what is the mutual between these two mesh? So that will be your minus R2, and the last one is of 2 2. So here in this mesh 2, we can see that this R2 and R3 are the part of it. So we will sum the resistance values and write it over here as R2 plus R3. And on the right hand side we have to write down or do the algebraic sum of the voltage source that is present in the particular mesh. So this is the position of the mesh 1. So this is the position for mesh 1. So for this position for mesh 1, we can see that there are this V2 which is from positive to negative, and the current direction for V1 is from negative to positive. So it will be V2 minus V1. Similarly, for the second mesh, we can see the direction is from positive to negative, and for this V3, and for this V2 the direction is from negative to positive. So therefore it will be minus V3 So first one is of V2 minus V1 minus V2 V1 minus V2, and this one will be V2 minus V3. So this way we can write down the means we can apply the mesh current method, and we can directly write down the mesh current equations in matrix form. Now after it we solve the matrices to get the unknown unknown variables, that is VA, VB, VC, and for the mesh the unknown variables I1 and I2. So this way we go for applying that node voltage and mesh current. So with this I will conclude the today's class. Thank you.